threaten me with a good time, I know, but all right. So, so the plan for today is I wanted to show you just like my talk from today, from this morning, which is kind of relevant to actually what I was gonna do anyways. And it's kind of fun. I did like I think a fun analysis last night, kind of a little bit inspired by the fact that I'm teaching the class right now. And then we'll go back. So we'll talk a little bit about causal inference. And if there is time, we'll start talking about neural networks. So I'm like, I do want to kind of wrap up the inference part and start doing machine learning. Like, to be honest, I think I do think that kind of the causal, well, like the inference thing is kind of important because like if you're doing data analysis, oh, hello. So like if you're doing data analysis and you don't have kind of the causal stuff or the inference stuff nailed down, like the analysis like kind of means nothing. So I hope you agree that it's like at least a little bit interesting. And I am gonna do a demonstration. Why is it central projector? All right. So this is my talk from this morning. So the slides are kind of like just from the talk, which is aimed more at kind of statisticians than students, but I think close enough. That was in Hamilton. This is I didn't actually make it to the botanical gardens, but apparently that exists in Hamilton, Ontario. If you want to. So okay. The motivation for this talk is this paper from the year 2000, which is called Storks Deliver Babies, P equals 0.008. So it's like it's published in a journal called Teaching Statistics. It's a pedagogical paper. It's not a real claim. And the idea there is basically like this. So you can plot, actually let me just show it to you. So you can plot the number of babies in the country versus the number of storks in the country, and try to do linear regression on that. And as it happens, the p-value is significant. And the lesson of the paper, or the supposed lesson of the paper, is that p-values can be misleading. Okay. Oh, U of T apparently doesn't buy you that, but I think there is like free versions on Google Scholar. Okay. Praxis.dk, close enough. So I think that's probably pirated, but that's okay. So yeah, so that's kind of the headline graph. So you have so it says birth rate, which is like its own weird thing. And here you have number of stork breeding pairs. And then the claim as well, like this is significant. So don't run linear regression and just interpret p-values willy-nilly, kind of think about it. So I think this paper, like, I do not think that storks actually deliver babies, but I think in other ways, this paper is completely wrong. So this graph, to my mind, is terrible because here what they're doing is they're plotting birth rate, meaning, well, technically it says birth rate, it is number of babies, but rate implies per capita. So plotting per capita versus the number of storks is completely wrong. Like if your idea is that storks deliver babies, then the effect is like on the total number of babies not on the number of babies per capita, right? So that's it. Now, when they run the regression, they actually do run it the right way. So the actual number of babies in thousands versus the number of storks. And then here's the conclusion of the paper. So they say, well, like, you shouldn't trust it. The most plausible explanation is the existence of a confounding variable, and they suggest that it's the area of the country. So the paper itself suggests just like add the area of the country as the confounding variable, and indeed, if you do that, the thing goes away. But that is silly, right? So the model that they suggest is like babies is like A0 plus A1 times area plus A2 times storms. There is no way of, well, plus alpha. And so, like, there's no way that this is right. This is like an additive model. So they're saying that, like, you know, you take a weighted sum of the area of the country, the number of storks in the country, and that somehow predicts the babies. There's no mechanism that could possibly do that. And yet that is what they suggest. This is a famous book called, so it's called like Calling Bullshit. It's based on a course at the University of Washington. There's a book, there's a course on YouTube, stuff like that. They use this example as well. And again, for some reason, they suggest that, oh, like what's going on is there's like a country size, which operationalized supposedly as the area, and that affects the number of storks and also the number of babies. I don't know how that came about, but like in my understanding, that is not how babies work. And yeah, people say it. So I got the data and did a reanalysis of this important question. And here is what actually turns out to be the case. So this is linked and it's gonna load soon. So if you plot the correct kind of births per year, so this is per million people. So if you plot the right thing, so just birth per year versus number of storks, what you get is this. So here, basically what you see is Turkey is way off. Supposedly has like a lot of storks and also a large country. And basically, it turns out that if you take out this outlier, which you should, because the model here doesn't fit, like this is not a straight line plus Gaussian noise, because Turkey is like, which you should before computing the p-value, because here the model doesn't fit, then you get birth, then you get like a flat. So this is number of baby storks. So you get like a flat curve as you would expect. It's possible that in some countries the storks are just lazy, but like no relationship as it turns out. And to my mind, this is like way more of a correct analysis than what's suggested elsewhere, where basically they're saying just do this and somehow it's going to work out. So let me kind of do the takeaways. So like my takeaway, that p-value should never have been computed in the first place. Like I told you, you should not run a model if the model does not fit. Here, the model did not fit. If you can justify taking out the outlier, then you can do that, and then you can run it. And the suggestion in the paper and in sources downstream is like way off. I'm not just complaining about the paper in the year 2000, although I am writing a letter to the editor of the journal. I'll have like a better takeaway in a second. And then like yesterday I had another idea, which is like, okay, like if storks do not deliver babies, do obstetricians? So I got some data. So with Claude Code, it's not that difficult to scrape data for all 50 US states for the number of obstetricians and the number of babies in each US state. And here's what you get. So if you plot just like number of births versus number of obstetricians, then yeah, like there is a pretty clear correlation. Now, that is explained by not by the area, but certainly by the population of the states. So like more obstetricians, more babies, that just makes sense. So here again, like the additive suggestion from the 2000 paper and from downstream work is silly, but dividing by the population just makes sense, right? So like per capita. Now, if you do divide the births per, so like you can do per capita, you can do, so like the usual way that people compute fertility rates is they take like women 15 to 44 because that kind of makes sense. So that like, because there's like population structure, so like if everyone's older in the state, then there's going to be fewer babies because of that, stuff like that. So if you do that, then you get this kind of trend. And this is actually robust. So you could say, well, like, let's take out DC. DC is weird because that's whatever. It's like, it's a small city. There's no suburbs, stuff like that. But you take out DC, it doesn't matter. The trend becomes even stronger, arguably. And this one is, like, at least for this data, is real. So the R squared is pretty large. So the R squared is 0.36. R squared, if you remember, is the error, is kind of the error compared that you get from predicting here compared to just predicting the same rate in every state. So like 0.36 is respectable. The p-value is tiny. It's a real trend. Now, what do you conclude from this? That obstetricians do not deliver babies? Well, that would be a weird conclusion. I did try midwives for the record. You get the same kind of graph. And I did try, well, like maybe like obstetricians are like coded as gynecologists. Maybe there's like abortion rates, whatever. No, like abortions work the same way. I explored this. I explored this in depth. So in relative depth. I used to specialize in storks only, but yeah. So would you conclude anything from that? Well, like obviously you wouldn't, right? There is no, like, if there is a causal connection there, it's very roundabout. There is like all sorts of other factors. And yet, what I suggested in my talk today, and what I think basically like anyone would believe, is, you know, if it went the other way, so if it were that the number of babies per capita is correlated with the number of obstetricians per capita, it would be just a textbook exercise, and nobody would give it a second thought. It's like, whatever, like, makes sense. Like, it could be flat, it could go up a little bit, I think anyone would say, and nobody would investigate it further. And that suggests a problem, right? So on the one hand, we have, I don't imagine that you saw the Storks Deliver Babies paper before, but it's like famous in statistics education, and it's like in many textbooks. And like nobody really checks the story here. Everyone kind of hand waves it. Again, if it turned out to be the case in my analysis yesterday, that, you know, a little bit more babies, a little bit more obstetricians, people would just say, makes sense. You could put it on like in the textbook as an exercise. People can run it. So that's a problem, because that implies that you basically shouldn't believe anything that's in the statistics textbook. So one possibility is to stake out a kind of maximalist position and to say, okay, like you have a linear regression or any kind of regression on just observational data. Well, that just never licenses any causal claims. So obviously, storks cause more babies is absurd. But anytime that you have just correlation from observational data, you could say, well, like if the title says storks deliver its babies and you only have a regression, you don't even need to look at the details. You know that that just is not licensed by that at all. And that's a possible position. Again, you can say there is no fit, just too bad. You can't run the model. And I think that textbooks should have exercises where you're given the data set and there's just nothing you can do. There is no justification for removing the outliers. It's not a straight line. And you would say, well, too bad. I don't know what to do about it. I just cannot do the linear regression here. Almost none of the textbooks have exercises like that. You can remove outliers. So this is still the maximalist position. You can remove outliers, but not the way I had done it just now, but only if you have a justification for removing a particular outlier. So what I had done in the storks deliver babies analysis was kind of a compromise, because I said, well, like Turkey ruins my straight line. So I'll just remove Turkey because whatever, I don't know, maybe the number of storks in Turkey is like a typo or something. Well, maybe, but maybe not. Maybe Turkey is actually important and is part of the trend. I don't know. I don't know anything about the storks population in Turkey, right? The final kind of thing is you could say, which almost no one does say, is if you don't have a mechanistic model for what's going on, then just too bad. You do not get to run a model to try to determine causation. So the example with the storks would be, well, like if you don't actually have a mechanistic model for how storks deliver babies, so you look into, so for example, you looked into it and you figured out that a stork just like cannot carry a human baby because it's too heavy, right? Well, too bad. Like it doesn't matter if you can run a correct regression. You just don't get to run it because the mechanism is not there. That would also imply that if I don't have a very concrete story about how obstetricians cause for there to be more babies, well, maybe I don't get to run that regression, even if I'd really like to, because I would get just something spurious that's not causal at all. Now, if I'm being an extremist like that, that would imply that a lot of social science is just bad and wrong. And I think some of social science is bad and wrong, but I would not go as far as to say, well, just like don't do anything unless you have a really kind of physics-like experiment where you have a precise hypothesis about the mechanism. Like that's extremist and bad. At the same time, I don't know that there is a solution to that, right? So I don't know that it's reasonable to say, well, like if you don't have the exact story about what's happening with obstetricians and babies, and like to be clear, you could have all sorts of stories, right? So you could say, people say in the US, well, like if you had, better maternity leave policies, then you would have, a higher fertility rate because people would say, well, like I can afford to have another baby or something, right? So like people say that. And that's a story that could happen. You could always also say, well, like it has all sorts of implications and those sorts of things. You don't know what's going to happen. So you could say that even that story, which is kind of plausible, that, higher, better maternity leave, people would be, more inclined to have children. So like maybe not. But yeah, so like you have to have some kind of standards, but you cannot be maximalist about it. So what to do about it? So I think, and I'll kind of do the model building today as well. And we started doing model building the other week as well. I think kind of part of the solution is just a lot of epistemic humility. So epistemic means, do people know the word epistemic? So epistemic means like relating to knowledge, to the acquisition of knowledge. So epistemic humility would mean kind of humility about what you can know and what you can conclude. But it's like humility, it's not like nihilism where you say, I don't believe in anything ever. It's more like every study, well, like, maybe it's correct, maybe it's not. And I think people should have more what I call epistemic humility, which is like, not to kind of completely deny anything because it doesn't follow the rules exactly, but also to know that you're kind of always bending at least kind of the maximalist rules about what you get to do when you're doing any kind of observational study, and even any kind of kind of randomized experiment as well. But like, to be clear, like, this is justified by the math, right? Like, this is not like an opinion. Like, the opinion would be that you have to follow it strictly. But what's not an opinion is that you absolutely can have all sorts of things that appear real as trends where it's not because X causes Y. Like, that is completely true, right? And do people understand kind of the last point? So the point is kind of like this. So what we mean by mechanistic, so people use it now in machine learning, actually, but people use it, when they do pharmacology research all the time as well, where the idea is a mechanistic understanding of how a drug works, for example, would be on the molecular level, you know what it's doing, and you know how it affects whatever physiology that you want it to affect, right? So if you're doing a study where you have a mechanistic understanding of a drug, so you have like some hypothesis about like, this is what the drug does, and then you say, well, like, if I'm right about that, then I have a prediction about what the data is going to look like when I collect it, and then you can test it. The reason this comes up is with lots of drugs, people have no idea about the mechanisms, right? So for most, for most kind of, especially in mental health, but not just in mental health. So like, nobody knows exactly how the brain works. People know the immediate effect of a lot of drugs that are prescribed for mental health conditions. So for example, you can like suppress the serotonin receptors, and people hypothesize that that is why some depression drugs work, kind of. But at the same time, nobody really knows how serotonin actually affects depression, and it can affect it either way to people's understanding. So a lot of a lot of kind of pharmacological studies, they do not really have a mechanistic understanding. They just have, we know that this affects something on the molecular level. We think this would have effect on patient outcomes, but we don't really know why. And people still do those studies. Anyway, all right, so that's like this. So I wanted to do another case study also from the Statistical Society of Canada presentation, but kind of longer ago. So this is like the time that they got, well, the first time, I guess, that they got on TV. So I was doing, so this is kind of related to what we were doing last time. And this was a consulting project for CBC. So this is what was going on here. So basically, every city, it's done on the municipal level, sends out inspectors to restaurants. The inspectors report major and minor violations in those restaurants. And then this data is collected on the municipal level. So what CBC wanted us to do was to rank the restaurant chains by food safety compliance. So basically, like, how many major violations, how many minor violations did every restaurant chain have? And then they wanted like a ranked list. So the issue is that different cities train the inspectors to different standards. There's like way fewer violations in whatever Calgary than in Toronto. And not because Calgary is necessarily like that much more compliant with food safety regulations. They just have different standards about what it means to report a violation. But it's also like probably true that it's not the case that in every city, the average level of compliance is exactly the same, right? So there could be systematic differences as well. So what they wanted from us was a list of restaurant chains by how much they comply with food safety regulations. What we wanted to do is do a good job, account for the fact that different cities have different standards, but also produce a unified ranking rather than just ranking within each city, which you could, of course, do by just counting. So this is what the data set looks like. Whatever. So this is like incident report, like individual incident reports for every location of every chain. So this is like the importance. So they report like whatever. So this was like a kitchen cleanliness issue. There is like all sorts. There's like pest control, whatever, right? So yeah, so like another thing was that in Vancouver, it wasn't, so they actually, CBC actually, I believe at least, so they had like reports that were just verbal rather than counts of violations. So based on the verbal reports, they like coded it as this kind of violation, that kind of violation. Okay. So how would you rank chains, so restaurant chains in a single city? Well, you could just compute the average or like expected number of major violations. So we decided that minor violations don't count together with CBC. And then you could say, okay, like we measure how many violations you have for each location, and then it's like it's like flipping a coin. So you have a confidence interval around the estimate of the probability of a violation on every single visit. And then if the confidence intervals overlap, you could say, well, like the ranking is, you know, like it could change. It could be that the changes got unlucky because there were just few inspection visits and they found violations, you know, just by accident. Right. So that's kind of the source of the uncertainty in the ranking. So now we want to combine data from multiple cities. So we had Toronto, Vancouver, Calgary, Ottawa, and Regina. This is like the picture that I came up with it. So this is like the famous towers for each of the Canadian cities. They look like they're the same height. Of course, like the CN Tower is like way taller than whatever, like the Peace Tower in Ottawa. I don't actually know what this is. Yeah. Okay. So here is kind of an idea of how to do it. So you want to say, okay, we want to explain what we rank by. So here's the explanation of what we rank by. We're saying if we send a City of Toronto trained inspector to a random location of the Tim Hortons in whatever city, what would they assign? So that's what we rank by, right? So on average, like I'm a Toronto inspector, I go into the Tim Hortons location in whatever city, and the question is like, how many violations on average do they find? So that's the measure. So, okay. So here's how we do it. So we are saying, all right, we'll define a number, we'll define a probability distribution for the number of violations. So like it ends up being just a regression. But what we're saying here is, you know, what's going to be the probability distribution of the number of violations? Well, it's going to be, so Poisson is like the probability distribution with this average. and then there is like a standard deviation, whatever. So the parameter here is we're saying so we're saying the mean number of violations that you'll find is X of this. So the reason this makes sense is one, it works out numerically, but two, it kind of makes sense that it should be multiplicative, right? So this would be equal to XCX A chain XB chain. So that should be, but this is how the exponent works, right? And it kind of makes sense because what we're saying, because what we're saying here is on average in Toronto, it's going to be this much plus a coefficient that's specific times, a coefficient that's specific to Toronto, right? And it kind of makes sense. Like you wouldn't say in Toronto, they always add one more violation. You would say that what would count as like 1.5 violations in Vancouver is the same as like 2 violations in Toronto, with a ratio of like 2 to 1.5 rather than an additive thing, right? So, okay, so this is what this is saying. And what we're doing, so there's like numerical details, but this is basically what we're saying is find A chain and B city for each chain, each city. So I went through what happens with B city. A chain is kind of the same, right? So what we're saying, and here you could imagine an additive model, but again, like what you're kind of saying is if like second cup is twice as dirty as Starbucks, which incidentally it is, then what you get is well, like this just multiplies, right? So for every violation in Starbucks, you would expect don't sue me. So there is like actual data at the end of the slide. So for every violation in Starbucks, you would expect to find 2 in second. And it again kind of makes more sense than, you know, whatever you find in Starbucks, there's like a +1 in second cup. Second cup does actually have like a specific issue of leaving sandwiches out for too long, or at least they used to have. Do not sue me, or at least they used to, and that counts as a violation. So like they had like a specific issue. So okay. So that is kind of how it works. So there is a way, which I'm not going to get into, of again obtaining uncertainty for each of the coefficients as well. So how do you rank those things? Well, you just look at A chain, right? So the idea is if you know A chain for each of the chains, then, and you know B city for each of the cities, then you could say, well, for every chain city there, I can now predict the average number of violations that I'd expect if I just walk into the store. Right? And then you just rank by the chain. There is uncertainty around this coefficient. There's ways to get that, which I'm not going to get into. And then you can have kind of uncertainty. This is the ranking. So this is like the major violations per inspection adjusted to Toronto standards. So as I was saying, did I like understate how much dirtier second cup is than Starbucks? Yes, I did. So they might have improved their game. So like they had like major issues apparently. And kind of makes sense. So like whatever else you would say about Starbucks and Subway, they do seem like they have like good compliance standards. So okay. I'm not going to do the this model now because this is like getting a little bit in the weeds. Cool. Does this make sense? All right. So yeah, so I think if you go to my website, there's like a screenshot of the formula somewhere, I think. Yeah, so this is like yeah, so this you can't quite see it, but you see like n violations, and then there is like Poisson something. So that was on TV for like a few seconds. Oh, there it is. Yeah. So yeah. All right. So that's like this. Okay. So this is that. So that was like more of a case study. Like not testable, I think, so far, given that was just telling stories. So I now want to talk about causal models. So we already actually, did we see this comic? I think we did. Oh, no, I don't think we did. Yeah, so like I used to think correlation implied causation because statistics class, like it helped, maybe. So, yeah. So, okay. So the textbook chapter that I'm taking this from is linked from the course website. So this is called a directed acyclic graph. So graph just means kind of things that are connected by arrows. Directed means that there's arrows. Acyclic means that there is no like circles that you can make with the arrows. So this is used to represent causal structure. I'll explain in a second why it needs to be acyclic. So this is like a slightly fake, simplified story about what you might observe. So each node here, so a node is like a rectangle, represents a variable. So smoking could be 0, 1. So 0, the person doesn't smoke. 1, they do smoke. Yellow teeth is like, do they have yellow teeth or don't they? Whatever, like as a binary. So similarly, you can imagine that there's like levels of tar in their lungs, which is like above a certain threshold or below a certain threshold, or you can imagine it being continuous. And then do they have a cancer diagnosis or do they not have the cancer diagnosis? So in this story, at least, so this is like a simplified story, is, well, like you have so arrows, sorry, I did not say, represent causation. So here, the idea is that if you smoke, then the smoking can cause yellow teeth. And equally, smoking via the fact that there is tar in your lungs can cause cancer. But also another thing that could happen is if you live in a building with asbestos, that can also cause cancer. So this is what this picture represents, is if tar in lungs is high, but also you lived in a building with asbestos, both of those can cause cancer. So the arrow represents causation. All right. So this is just like a picture of what we believe about the world, but it's also a picture that represents how we can generate kind of fake data, similarly to what we had done the other week, that would kind of look like the real data, right? So the way we would generate it is we would first generate smoking and asbestos. So those are not dependent on anything that we see anywhere, right? And then once you know whether we decided that this person smokes or not, we can generate yellow teeth. Once we know whether they smoke or not, we can generate tar in lungs. And then once we have tar in lungs and we have asbestos, we can generate cancer. Does that kind of make sense? Do people want, okay, like I'll do an example of kind of coding this, but later. Okay. Why do we do this? Well, because it can help with inference. I'll show you how in a second. So one thing that you can get, so this is kind of an assumed structure that you get from just kind of from science, is okay, so tar, so statistical independence, we are not going to like technically cover the math here, but you would say, okay, so like tar and asbestos, those are not related in any way, right? So like when you're generating this kind of data, which is supposed to look like the real world data, the way asbestos is generated and the way tar is generated, they're not related in any way, right? So on the other hand, and that is going to come back to the story we're telling before, tar is not actually independent of asbestos if you know cancer. So what I mean by that is that if you know that this is how the data is structured, and if you know that the person has cancer, then having information about whether they were exposed to asbestos actually influences your probability of estimating whether they have tar in their lungs. So that should be a little bit intuitive. I'll walk you through the intuition, but it should also be a little bit surprising because we're saying, okay, asbestos is about like your history, like where you lived, whatever. Tar in your lungs is about whether you smoke. We said that they're generated independently, and yet if you know that the person has cancer, then knowing whether they were exposed to asbestos influences your estimate, sorry, for whether you would find tar in their lungs. So here's the intuition. We're saying, okay, like imagine that you know that they have cancer and they were exposed to asbestos. Then you're saying, okay, like the fact that they have cancer is already explained by the fact that they were exposed to asbestos. Having tar in your lungs is rare. So there is no particular reason to think that that they were exposed to tar, because like the cancer is kind of already explained, right? So that's like it's true. And what this would imply is that if you just take the people with a cancer diagnosis and you look at the relationship between tar in lungs and asbestos, what you would see is a negative correlation. On the other hand, if you take the general population, what you expect is no correlation because they're generated independently. Right? Is that intuitive to people? Is it not intuitive to people? So let's kind of do another famous example. So imagine that you're just looking at people who were admitted to graduate school, right? So in general, you know, like they have like a high GPA and a high GRE both, right? But imagine that you're just looking at people who were admitted. Then if you're looking at people who were admitted, Well, they were admitted on the basis of the sum of their GPA and GRE or something like that, right? So what you would expect is that if you know that someone has a higher GPA and they're in high school, that says, okay, like they have a high GPA, so like on average, they'll have a lower GRE, right? On the other hand, if you look at the entire cohort, what you would expect is that, you know, higher GPA is higher GRE just because everything is kind of positively correlated. And you do, in fact, sometimes see, like with a very high cutoff, a thing where, like, if you're good at something, that explains that you're admitted, and that kind of lowers the estimate for how good you are at other things. And I think like sometimes people, so kind of the GPA and GRE, that's kind of true in some data sets. Sometimes people say, you know, some people think that like either you're whatever good at math or you're good at humanities. And that might be true if you're in a highly selective place where if you got admitted into the selective university, it must have been on the strength of like one of your skills. So you would expect that people are either good at math or good at humanities if they're selected on the sum of their skills. On the other hand, if you look at the entire population, it's actually like generally not true. Like in general, like you're good in one subject, you're good in another subject. That's the usual situation. So sometimes so people's intuitions about kind of this kind of there's math people and there's humanities people are maybe based on being like in the selected class where in order to get there, you had to be good at something, but not necessarily at everything. And then if you're good at one thing, well, that explains why you're there. So you don't need to be good at the other thing. So hopefully that kind of gives you some intuition for what's going on. Sorry. Another kind of deal here. So you have yellow teeth and you have tar. So those are not independent for the obvious reason. If you smoke, you would both have yellow teeth and you would have tar in your lungs on average, right? But on the other hand, if you just look at the people who smoke, it reverses, right? So for just the people who smoke, well, like there's some probability that you have yellow teeth, which is heightened, and there's some probability that you have tar in your lungs, which is also heightened. But if you're just looking at the smokers, then yellow teeth and tar in lungs, according to this diagram, are actually independent for the smokers. Equally for the non-smokers, they're independent. So the relationship of yellow teeth and tar in lungs is because they're caused by smoking. But for the smokers and for the non-smokers, they're actually independent. Does that make sense? So what would that imply about regression? Well, it's that if you try to predict tar in lungs based on, so this is tar and this is yellow, whatever. So in general, it would look like this. So this would be like for all. But for smokers, they're not related, right? So like you might imagine that like this would be smokers and this would be non-smokers. And the point that they're making here is that those are kind of reversed, right? So the non-intuitive thing that we were saying here is for cancer patients. So in general, for everyone, tar in lungs and asbestos are not related. But for people, only people with cancer, only people with no cancer, they become related potentially, right? In this structure, it's the other way. In general, yellow teeth and tar are related, but you take just the smokers, just the non-smokers, they become unrelated. Does that make sense? So this is not a claim about medicine. This is a claim about like if this is what the data looks like, then that's what's gonna happen. Make sense? All right. Um, so to be clear, this is like a disclaimer. So I'm not saying so anytime that they say not related, they're definitely not related. But anytime that we're saying, well, like R and yellow are correlated, well, they might or might not be. So the relationship, like it might be that there is a relationship that's represented by the arrows, but that relationship might be just nothing, right? So the arrow is kind of not, there's definitely a strong relationship. It's like there might be a relationship. Um, so okay. Does that kind of make sense so far? All right. Let's take a 10-minute break and then we'll do some coding. Or okay. Do you want a break or do you want to like let's do a break. Sorry, I'm tired. Yeah. So back at 3:35. It's 3:35, but this person is still not here, so I'll wait for them. Yes. For like 1 minute. All right. Hey, yeah, sorry. So I sent you guys an announcement. Yeah, I'm sorry. My plan for the many projects was like clearly not working. And I do want people. So, like, we're gonna continue. I'm gonna, like, the commitment was that you should be able to do everything in the 7 weeks if you'd like to, and I'd like to stick to that commitment. At the same time, I want to enable people to focus on the course project right now. So what I'm going to do is I am going to post a combined mini project 3-4, but you can submit it in July. I don't care. And I would like for people to focus on kind of making progress on the course project. So I'll post guidelines about the kind of interim thing. Uh, kind of, I hope to like both grade the tests and post the guidelines like certainly before the lecture on a Friday. We can discuss on Friday kind of the details. Essentially, what it's going to be is I will ask everyone to schedule kind of half an hour with me to tell me about the progress and to show me what you've done so far. The expectation is that you would have collected, if like not necessarily all the data, but like something just to show that it's possible to do something so that you're not stuck, and that you've read uh, kind of 5 related papers and could summarize them. Like that's it. And then what I want to do is just discuss with everyone the progress, just like to give my thoughts about what to do and to kind of redirect people if necessary. It's not usually necessary. It's just good to have a checkpoint to make sure that everyone's on track. And also, like, sometimes I have good ideas. Like sometimes I end up publishing with people if we kind of figure out a good idea together that we can work on. That's not the expectation. The usual thing it doesn't happen, but that's also an opportunity to kind of see where we are. So that's kind of the idea. I'll post the exact format and just a Calendly thing so that we can just talk to everyone for like half an hour. So that would be the idea. In general, kind of I don't think I'm not actually sure. I think we do have a final. I think the presentation format is the interim one. It's not the final one, but we'll talk about the final one as well. We can do like a showcase if people want. At the same time in August, like probably it's not going to be all of us together. Maybe you can do something online, but anyway, we can discuss it later. And like honestly, I don't want to like make people do anything that's not kind of substantive work. At the same time, yeah, so like we'll talk about like the final project later. Okay. So, sorry, I woke up at like 6 o'clock today and like prepared to talk for the conference. And big day. Okay. So what I want to do is take this and just make it concrete by writing code to do it, and then also show the explaining away the construct, which might not work the first time. It's usually pretty subtle. So I want to basically like generate one person. So that's going to be a function. So basically I want to make this concrete. So how do I generate the person? So like we said, smoking and asbestos are not conditional on anything, right? So that means that you just generate them randomly. So we would say, okay, so smoking is either 0 or 1. So if you remember our binom, so we're just generating one person. And we'll have like a probability of smoking. So that would be a parameter, right? So similarly, asbestos, you generate like this. And again, we'll have a probability of asbestos. So those are the unconditional things that are just random, not related to anything. So yellow teeth depends on whether you smoke or not, right? So we'll do like yellow. So R has an if else kind of deal. So you can do like condition and then what happens if yes, what happens if no. So the condition would be smoking is 1. And then like we'll say like if yes, I don't actually know the real numbers, I'm making things up. So like 0.8, 0.2, whatever. So this would be like yellow is 0.8 if smoking is 1 and 0.2 if 0. Does that make sense? So I'm just making it 0 1. Like you can do it with the if else, it's just like nicer that way. You can also do like a big if else. All right. So tar works the same way. And we'll just do the same probabilities. They're like obviously made up. So to be clear, like those are sorry, so I didn't sorry, so this is like the probability. So I'll say like probability yellow and I'll say probability tar. And then I'll generate the actual yellow. So this would be like our binom. Again, n equals 1, size equals 1. Probability is prop yellow, and then tar, I'll generate the same way. So this is like this. I don't know if this skill is useful in the age of large language models or not, but I imagine that many of you are slower than me at typing this kind of thing. So just like in case you don't know, so on a PC, if I press Shift, press Home, the Home button, that selects, and then I did Control C, Control V. So that is how those lines were generated. On a Mac, this is a Command Shift right to Command Shift right to do this Command Shift. Sorry, this Command Shift right, Command Shift left, Command Shift left, and then I do like Control C, Control V. So all right. So that's like this. So asbestos we already generated, and now we have cancer. So cancer is the interesting one. So cancer is caused both by tar and by asbestos. So we need to figure out some kind of formula that would work for that. Sorry, it's like there's like a choice of like either you do something that doesn't matter or you do something that's like important, but because it's important, it's kind of like sometimes people would have association with it. It's okay. So the probability for cancer. So what can we make it? So we want the probability to be higher if the person was exposed to asbestos, and also higher if they have tar in their lungs. So if you remember, we had this nice logistic function which produces a probability. So I'm gonna use that, and I'm gonna say, okay, so I'm gonna add like 0.5 times tar, and I'm gonna add 0.5 times asbestos. And so that it's not too large, I'm going to subtract like 0.7 or something. So the convenient thing is, if you remember, this function always produces a probability because it always produces a number between 0 and 1. And then what I'm doing is I'm making it so that tar is higher, the probability is higher. Asbestos is higher, the probability is higher. And it's always probability. So to be clear, it's made up, but I'm making it so that it at least kind of makes sense. So now we'll produce cancer, and again, we'll do like R binom. Make sense? So the reason I'm doing this is just kind of to operationalize what we mean by that graph. So hopefully it's a little bit helpful, but also it's going to allow me to do kind of interesting experiments. So, okay, so that ran, so I can say generate person. So let's say probability of smoke is 0.2, probability of asbestos is 0.3. I did not actually return anything. So I'm going to say smoke. So I'm going to say I'm going to say like just going to return like a smoking and asbestos and yellow and tar and cancer. So I run this, and I'm gonna get like a different number, a different binary variable every time. I can get a large data set. Sorry, the other way. So that's going to be like this. So this is like a matrix where we have whatever 5 rows, so corresponding to each of the variables, and then columns that correspond to the patients. So let me just produce a data frame from this. So that's more like it. So this is just transpose. So T stands for transpose. You do not need to know that. So like I want to produce a data frame from it. So I will. So I'll convert it to a data frame like this. So I'm going to say data frame is this. So now it's a data frame. So one issue here is that the columns are not named. So I'll name the columns. So this is going to be df. And then in R, you can just say like call names of df, and you can just give the names of the columns that you want. This is possibly not the best way to do it, but whatever. So I'm just going to give it a vector with, oh, that's nice. So, okay. I know why I did it, but okay. So tar and cancer. So if I run this, now I have a data frame. And if I look at the head of the data frame, that is now an actual data frame with variable names and stuff. All right. So, all right. So now I get to check the claims that I've made before. So the easy claim is that smoking should be unrelated to asbestos, right? And indeed, like there's, well, no reason to expect that it would be, but we'll check anyway. So I'll say, I misnamed it. Okay, I'll abs, whatever. So abs, and then you have smoking, and we'll say data is equal to df. And indeed, what you see is that smoking is not seemingly related to asbestos. So the convention is you look for a p-value smaller than 0.05. This is not smaller than 0.05. They're not related. That's great. So what would we expect to be related here? So obviously, like smoking and yellow should be strongly related. We rig them up so that they would be, right? So let's try that. And they are indeed strongly related. That's what you would expect. So so we claimed kind of two interesting things. So we claimed that yellow and tar should be related for the entire population, but not for specifically just smokers and just non-smokers, right? So let's check that that is true. So we're saying tar and yellow. So tar and yellow, as you see, strongly related, although the R square is pretty small. So that means that the relationship is pretty random, but there is a trend. And the trend is if you smoke, then you have tar in your lungs and your teeth are yellow. The claim was that if you just take the people who do not smoke, then that relationship is going to go away. So I'm going to say data is df smoking is equal to 0. So this is one of the way to subset. And indeed, there is no relationship. So if you just take the people who smoke, again, there is no relationship. So the usual thing that you hear when people talk about epidemiology is, well, just control for that. So I'm kind of doing it manually here. I'm just saying, well, just look at this subset and look at that subset. The more usual thing that people do is they say, okay, like tar yellow, but control for, so try to predict whether they have tar in their lungs or not, based on whether they have yellow teeth or not, but people say control for whether they smoke or not. So the usual thing that people do by default is the thing I criticized before with the storks and babies is they just say, well, predict whether they have tar in their lungs based on whether their teeth are yellow and based on whether they smoke. With the idea being that if the causal structure is what's drawn here, then smoking should predict it, but tar should not. even though it's the entire population. So let's see what happens. That did work, right? So you see that this coefficient is basically 0. So yellow basically has no relationship now to tar, but smoking does predict, and with a very small p-value. So what you would expect. Does that make sense? So like it should, hopefully. So the magical thing, and it's so magical that I'm kind of vibing the coefficients here. It might or might not work, but the magical thing is this one where we say the explaining away. So if the person, if for the people diagnosed with cancer, people not diagnosed with cancer, it should be the case that tar and asbestos are negatively related. Let's see how that works out for us. So I'm going to say tar asbestos. Not related. That's great. So the claim is if you just look at people with cancer, that's going to be different. And it's not. So what I'm going to do is I'm going to just try again. But so like the issue is that this is like a very weak signal. So what I'm going to do is I'm just going to up the sample size so that they can detect it. And this is, again, by the way, an illustration of kind of the pitfalls of statistical analysis. Like, I know from math that this is right, so I'm going to push it until it works. But we had 10,000. I'm like, okay. I'm just going to like increase my sample size by a factor of 100 and hope that works out for me. Those are fake people, and yet it takes a while to develop. It takes a while to run. I really hope it works. Oh, okay. All right. Aha. So, so, so as you see, not a huge effect, but we did find, as predicted, a negative coefficient between asbestos and between asbestos and tar, for if you happen to know that that the person has cancer, even though those are like independently generated. Kind of close. Does that make sense? All right. So I'm gonna try something dangerous here and do a sanity check. So, like we mentioned, if you have a huge sample size, any effect is going to be significant. So we got to check that there is no correlation if you don't subset. I really hope there isn't. There isn't. Yeah. And in fact, the sign flips, but it's not significant. It's nothing. So as predicted. Cool. Makes sense. All right. So that was kind of an exercise. I'm gonna try to tell you about how you actually work with this kind of thing to do inference, because so far everything was fake. So I was talking kind of informally about causation without actually defining what causation means. There's like whole books of philosophy written about what the tree means to say A caused B. So here's one way to define it. So it's kind of via what's called a counterfactual. So we say that A causes B if the situation is that B would not have happened if A had not happened, right? So what we mean by causal inference in this context is we have empirical data and we're trying to say, well, like A did happen, but if A did not happen, what would have happened? So we are answering always a counterfactual, which means that we're answering something that's not actually in the data. Okay. So this is just kind of like an example. So what is the causal relationship between exposure to asbestos and yellow teeth? So if this is how the world works, then the answer is that there isn't one, right? Because asbestos is generated just using our binom. And then yellow teeth is generated using smoking, but smoking doesn't have anything to do with asbestos, right? But in the same way that tar and asbestos, like we've shown, are actually negatively correlated if you know that cancer is 1, and they're negatively correlated if you know that cancer is 0. In the same way, yellow teeth, like by the same logic, are also going to be not independent of asbestos, despite the fact that there is no causal relationship, right? So that's the explaining away. So what that implies is that if we try to predict yellow from asbestos and cancer, we would potentially have a significant coefficient. So what it means to do causal inference is to say, okay, like even if you do have what appears to be a significant coefficient, how do you conclude whether there is or there is not an actual causal relationship? Does that make sense? So, all right. So how do you figure it out? Well, if you already know, then you have the answer. In general, what you have is just measures. So you have this kind of DF, whatever, and you're trying to figure things out. So the usual thing that you do is kind of the story with the storks. They're saying, well, yeah, like it might be that yellow and asbestos are correlated, but well, and like we were talking, like in cancer patients, but what if you control for smoking? Is what people usually say. And indeed, if this is the situation, then even if you just take the cancer patients, if you take the smokers separately and the non-smokers separately, then yellow and asbestos would become independent again. Does it make sense why? Just because, like imagine that you're just talking to smokers, right? So the smokers, so the smokers, like, that's what causes the yellow teeth. And then asbestos is separate from it, right? So you're saying, okay, like if you knew that you could control for smoking, and if it makes sense that you should, then you would be able to see that yellow and asbestos are related. So that's the situation of knowing what to control. But similarly, if you are looking at the relationship between tar and asbestos, then what you want to do is not control for cancer, right? Because if you control for cancer, what you would see is an apparent correlation between tar and asbestos, even though causally they're not equivalent. Like neither one causes the other directly or indirectly. So, okay, so that's kind of the usual way. So here is some, like, this is like not like easy stuff. I'm not going to do it formally again, but I do want to tell you about it. This is kind of the formal causal inference thing. And the idea is kind of like this. So I want to know the probability of yellow teeth if asbestos is 1, and also they have cancer, right? And if that's what they do, then what I'll find is, okay, like the probability of doing that, the probability that the person has yellow teeth, if I know that they were exposed to asbestos, is not the same as the probability that they have yellow teeth. But that is not to say that asbestos causes yellow teeth, because what happens is that those probabilities are different because of the explaining away component. Right? I can, however, say, okay, like what I actually want to find out is whether the probability of a person having yellow teeth is if I just make it so that magically you go back in time and you make them exposed to asbestos, is that going to change the probability? And the answer, if this is the picture of the world, is no. Sorry, that was like maybe not super clear. I'm going to try to do it again. So this we know, right? We know this, we just argued that if you measure the probability of the person's teeth being yellow, if they have cancer, it's different depending on whether they were exposed to asbestos or not, right? What I'm saying is that that's not a causal picture. So the causal picture is, what if we had a way of setting asbestos to 1 or 0 and measuring the probability? So that's like a counterfactual. So this is the do operator. So it's saying, if we could go back in time, it's the same person, but we flipped the switch and we made them exposed to asbestos. The claim is that if the world is as in this graph and we just set asbestos to 1, that should not change the probability of yellow. And that is kind of what you want to do if you want to do causal inference, meaning if you want to know the relationship between asbestos and yellow, whether asbestos causes yellow. Does that kind of... So far, this is kind of just a formalism. It's saying, if you want to know whether asbestos causes yellow teeth, you don't want to compare this and this. So you don't want to say, well, like, for the people who were exposed to asbestos, are their teeth more yellow? What you want to say is, for the people whom you made exposed to asbestos, kind of ex post facto magically, would that make their teeth yellow? Okay, so that's what's called the do operator. And what you want to do is ideally compare and this. All right. So can you do it? Well, in general, no. What I described is like a science fiction experiment where you have those people and you went back in time and you made them exposed to asbestos. You didn't change anything. That's not a thing that you can do in real life. However, and I'm gonna do it like in a very short way, because like doing it formally, like it's difficult and it usually doesn't work. It is sometimes possible if you have partial information about some effects, but not full information about all the effects, it's possible to compute those quantities. So I'm gonna give you just, you can read the chapter as well. I'm gonna give you just like a brief example. And even that example is kind of fake, but it's like slightly less fake. So here's the idea. So all of those things, so you have like health consciousness, you have like frequency of toothbrushing, have gum disease, you have frequency of exercise. So all of those things, in principle, you can measure. And for most of those things, there are studies that measure, how does health consciousness affect toothbrushing, and then how does toothbrushing affect gum disease, and so on, right? So, just like to tell you a story, that's, I believe, a true story that gum disease causes inflammatory immune response, and that in turn is believed to affect heart disease. So in fact, this graph is true. Health consciousness does cause toothbrushing. Toothbrushing does affect gum disease, and gum disease indirectly via inflammation can affect heart. Some people inflammation affects all sorts of things, including heart disease. All right. So the idea is kind of like this. If you have separate studies that are already done that estimate how health consciousness is related to this, and also how health consciousness is related to this, and also how health consciousness is related to whatever, the amount of fat and red meat that you eat and so on, then you can say, okay, I know each of those relationships. Those relationships are basically this kind of stuff, but with non-made up coefficients that you get from scientific studies. Then with this kind of graph, you can actually say, okay, I want to know the relationship between toothbrushing and heart disease. I can compute it. So the computation would not be based on this graph where you just take the correlation between heart disease and toothbrushing, because that's not actually a causal relation. That's not exactly the causal relationship because toothbrushing is caused by health consciousness partly, and then health consciousness causes heart disease to increase or decrease via other pathways as well, right? But it's possible to do a computation where you compute the probability of the kind of heart disease, the effect on the probability of heart disease with the do operator, where you kind of simulate going back in time and just force the people brush their teeth or not. So it's possible to do this computation. Details, I'm gonna give it in the homework a little bit, and we'll do an exercise later when the homework comes up, but also just details in the Shalizi textbook if you want to read it. Just so you know, it is in principle possible. Sometimes if you have older relationships from previous studies already. And this is in contrast to just looking at the relationship between toothbrushing and heart disease, which can be misleading because, according to this story, toothbrushing is caused by health consciousness, which also affects heart disease via other pathways that are not toothbrushing. In fact, probably mostly that. Right? Does that make sense? All right. Okay. So that's kind of the math way of just looking at the observational data and trying to infer causes. And sometimes it works. Mostly you just, there's nothing you can do. There is a straightforward way of computing what's the probability of Y if you set big X to small x, and that is to just do it, right? So you physically set big X to small x. That's what's known as an experiment, right? So if you do an experiment, then you can estimate the probability of Y when X is one value as the other value, because you just directly manipulate X. So that is possible to do. So one thing that's probably not obvious to people is, what do you control for? What do you not control for? If it's a truly randomized experiment, it doesn't matter, right? So if you truly say, okay, I'm going to force one group of people, that's a random group of people, to brush their teeth and force and like confiscate the toothbrushes from the control group, it doesn't matter. Like you can set everything else to be constant. You can not, as long as the groups are randomized and you randomly tell people you brush your teeth, you do not brush your teeth. In 20 years, we'll see how your heart is doing. That either way would work. So that is fine. So suppose you can't run an experiment, and suppose that the complicated math manipulation with the causal graph is not working out for you. Another thing that you can sometimes do is kind of do the regression right. So this is referred to as identification. So identification is a term that's more used like in econometrics than maybe in other fields. Identification refers to figuring out which variables are causing the variable of interest and which are merely correlated or not correlated though. So identification is like short for causal identification. So how do you do it? Well, you can do the regression right. So you figure out which variables to control for, which variables not to control for. Generally, the way you might try to do it is you might try to draw the graph according to your scientific knowledge of what's actually happening. And then, like we saw in the graph, well, you should control for smoking. You definitely should not control for cancer, because if you control for cancer, actually that creates spurious correlations. So another thing that you can do is use what's called instrumental variables. So this is a thing that earned the Nobel Prize in the 90s. So again, like I feel like you should know about it, but I'm not obviously doing it in detail. So here's an example of an instrumental variable. So let's say that you want to know whether smoking affects health in some way, right? So the problem is like you don't know. So like we argued, like maybe there is like a variable that's health consciousness, and that affects whether you smoke, but it also affects whether you exercise, right? And then you see that you do see that people who smoke are generally in poorer health, but you don't know, like maybe it's because they don't exercise, not because they smoke, right? So what would be the gold standard for figuring out things? Well, you could make one group of people smoke and one group of people not smoke, and then see how their outcomes differ. That's not an ethical thing to do. Also, they probably would not agree to do it. Okay. Sometimes you have what's called an instrumental variable that happens to be in the data set. So imagine that you have two jurisdictions, and one of them has high taxes on cigarettes, and another one has low taxes on cigarettes. So if whether you live in one jurisdiction or another is kind of random, then it's as if you have an experiment, because if the taxes are higher, you in the jurisdiction you live in, you are less likely to smoke. So it's as if you were forced not to smoke, right? So you might imagine that in order to figure out whether there is a causal relationship between smoking and health, what you would do is you would say, oh, like I'll look at the taxes in your jurisdiction and I'll look at your health. And then if the only thing that's different is the taxes, and the taxes affect the health plausibly just via smoking, you can make an inference that there is a causal relationship between smoking and health. Does that make sense? So there's like all sorts of other things. So you might imagine that you don't have this kind of instrumental variable. Like usually you don't, you have to get kind of lucky, right? But you might imagine, well, like, can I find people who are like very similar except along the single dimension? And then I'll say, well, it's as if they were an experiment, right? So like I find people who are like exactly the same, except like one smokes and one doesn't. And like all their other life circumstances are the same. So in that case, it's like almost like you're running an experiment. That's dangerous, but people do it. So this is called matching. So the summary is like sometimes you can do causal inference from just observational data. Obviously, like with a randomized experiment, you can always do it. But correlation really doesn't imply causation. Okay. Okay, so what is testable? So again, kind of what's going to be testable is mostly what's going to be on the mini projects. But basically kind of the stories are testable. So in the same way that they asked that it was on the previous test and that it was on test one, I can ask you to like make up a story where you can do causal inference, you cannot do causal inference. This code, so I'll put something like this on the mini project as well. So this kind of thing is in principle testable. So just like come up with some kind of model. I think kind of not much else. All right, makes sense. All right, cool. So I hope that was like kind of interesting and useful. You know, I do, so for the projects, I do encourage people to think about this. So especially if you're looking at observational data, usually what you're like, usually you're not, it's not really interesting to just have a correlation, but that's the usual outcome of like a course project or even like most research papers as well. It's like, well, we kind of see a correlation, like maybe there is a causal link there, maybe there's not. I do encourage people to think about the causal structure of the data. If you can figure out something interesting with the data that you do have, that always makes it more exciting and more interesting. So just to show you kind of one example of where it did work out for me, and again, like often it doesn't. So here, so if you look at improving, that would be this. So this is just a poster. Um, so so here's what we did. So this is like a case. So like case studies about my research projects, which weren't extremely successful. It's not in the test, but this is more like just a case study, an example of where things worked out. So we had kind of a data science course, and we had like a lot of teaching assistants. And then we were in, and the teaching assistants were doing kind of a research project on pedagogy on the side. And students had the opportunity to opt in or not opt in into kind of interacting with the teaching assistants. So, like all of them interacted, whatever, like they could sign up or not sign up. So we were interested in whether signing up was actually related to doing better in the course. So signing up for like the study that was like part of the course. So a concern was that, well, maybe you sign up because you're a keener. So of course, like keeners do better in the class. So just because people who signed up do better in the course doesn't mean that that was because they interacted with TAs. So an idea we had was, well, we do have all sorts of other measurements about those people. So because we also had an extra credit assignment, right? So we have like, so this is like test 1, test 2 in the class. So P would be the participation. And then we also know whether the students did an extra credit assignment or not. So the hypothesis would be that enthusiasm for learning or for the course, whatever, causes people to do the extra credit assignment, which really wasn't worth a lot. And also it causes them to do better on test 1 and test 2. And also it causes them to sign up for the study. So we had this causal graph, and then we coded this causal graph into the data, and it turned out, so this is like not an easy thing to do, but you can code this in and you can figure out the probabilities. And it indeed turned out that that even accounting for doing the extra credit, which indicates that they were maybe enthusiastic, participation in the study did increase performance in the first test. So you can do it. Yeah, like if you figure out some kind of causal structure and you want to do it, talk to me. So I did not give you nearly enough to actually do the math for figuring it out, but it's possible to do. And like it's not really math, it's more like computation, like you go with it. Does that kind of make sense? So all right. So that is that. Questions? All right. So I think we are a little bit short on time in this course, so I'm gonna start neural networks. So how many people have done neural networks like in academic work? Oh, most people. Okay. But some people haven't. So I hope you see something new here. But yeah, like if you've done neural networks, it's more going to be like light entertainment for a while. So all right. So I'm going to do kind of a brief introduction to artificial neural networks. So artificial neural networks, for people who don't know, are kind of particularly useful when applied to kind of large scale, high dimensional data sets, like images, videos, things like that. And I'm going to try to talk about artificial neural networks, both as a statistical model, so something that's like linear regression, model computation, and also kind of a biologically inspired model. So this is a picture of a neuron, so something that's kind of going on in the brain. So the idea is kind of like this. So neurons send out electrical pulses that affects the chemistry in the brain, and that activates other neurons. There are about 100 billion neurons in the human brain, and cognition is thought to arise out of neurons that are interacting with each other. So basically, a neuron firing that results in another neuron firing, and so on. So the people who took neural networks, do you know about the kind of the Hugo-Weasel thing? No? Okay. So this is going to be slightly disturbing, but it did win the Nobel Prize. So
researchers actually listened in to individual nerve cells firing. They didn't go well.
Sorry, just one second.
And rather by accident, one day onto the screen, and we found that the black dot seemed to be working in a way that at first we couldn't understand until we.
Sorry, hold on. Okay.
Make the cell
I am going to show you the cat. So this is a cat stuck in this apparatus. So I think that the cat is kind of fine, but it has an electrode in its brain. And what's happening is they're showing the cat those patterns.
In a way that at first we didn't understand until we found that it was the process of slipping the.
So what you hear when you hear the noise, that's the neuron firing. So the idea is that the electrode is attuned to a particular neuron, to a particular location in the brain with a particular neuron. And then depending on the pattern that the cats see, either the neuron is firing or it's not. So like what they're showing here is if there's like a diagonal line moving here, then the neuron is going to fire. If it's moving like this, it's not going to fire. All right. So in the visual cortex, so that's an area of the brain that's responsible for what's called at least kind of early vision. So that's responsible to just like responding to stimuli that correspond to your retina. It has been shown just like with cats, like now with apes as well, is that like there really are like literally like there is a neuron that starts firing if you see a particular pattern, right? So the idea is that neuron starts firing in the visual cortex, I believe somewhere over here, and then presumably cognition starts from that. So like you process the information further through neurons firing, activating other neurons, activating other neurons, and so on. All right. In the visual cortex, it's very clear that that's the case. In the brain in general, it's more of a theory, and this is the theory that I'm going to talk about now. But first, just like a quick review of supervised machine learning. So that we have all seen, maybe not in exactly this language, but the basic idea is you have past data, whatever, like you want to know what's in the image, you want to know what's going to happen with the customer, whatever. The goal is to predict with new data. So I kind of like this slide, so I'm going to do it. So the idea is kind of like this. So with machine learning, as we've seen in this course as well, what you do is you basically say, okay, like we have a training set. So expected input, expected output, expected input, expected output, and so on. And what we're trying to do with machine learning is we're just saying, okay, like we have this function, like this is linear. Well, this is kind of something like linear regression, right? And you're just saying, well, we'll just find the coefficients, theta 1, theta 2, theta 3, that predict well in the training set, and we hope that that's going to work on the test set as well, right? So unlike with introduction to programming, it actually works with machine. I'm very proud of this slide. It actually works with machine learning, right? So like you might imagine that in an introductory programming course, you kind of do the same thing where you start with some code that kind of doesn't work. I don't know how many people know kind of the weeds of Python to know the bug here, but there is a bug in the Python. So you're saying, like I'll just change the code a little bit. I'll see how that works out for me. That usually does not work. On the other hand, the magic with machine learning is that if you have kind of a guess about what theta 1, theta 2, and theta 3 is, you can see how well that works in the training set. Then you can adjust theta 1, theta 2 a little bit. And if it works a little bit better, then you keep that guess, and then you try to find better and better thetas, eventually find a good set of thetas. What we've done in this course is just to run LM or whatever in order to find those coefficients. In machine learning, people use something that's called gradient descent, which we're not going to get into. The point is, it's possible to find good coefficients for the training set and hope that they work well on the test set in a way that it's not possible to just try to modify the code little by little until it starts working, although many people try. Make sense? Okay, so this is just kind of the formal definition of what we've already seen. So we have some kind of rich data, maybe it's whatever, like this kind of deal. It's actually going to be more complicated with neural networks, but the same idea. And what you want to do is you want to find the coefficients theta such that you predict well on training set. I'm gonna skip gradient descent. Here's kind of a sample machine learning task that I'm going to work with for a while. Let's say that you have a bunch of photos and you know whose name corresponds to which photo, and you want to identify the photos of noted Canadian musician Justin Bieber. Okay, so people don't know. I believe this is him. Okay, so how can you do it? Well, first of all, what does Justin Bieber look like? Well, kind of like this, right? So it's a bunch of pixels. Each pixel has a brightness. So a lot of the time, the brightness is between 0 and 255. And then what's Justin Bieber to a computer? Well, it's a vector where you have the brightness of each pixel. This is for like a black and white picture. So for like a color picture, you have like red, green, and blue. Just think about it in kind of black and white. How do you do it? Well, so like if you have this kind of black and white or rather grayscale image, there is a brightness. So like this is like brightness 60, white is like 255, black is like 0, whatever. You can just convert it to a vector by just reading off the brightnesses of the pixels, just row by row. Are you with me? Okay. All right. So again, kind of formally, we have expected inputs X, we have labels Y. We want to find a function that maps the X's to the Y's well on the training set, and we hope to do well in the test phase as well. So, all right. So here's the simplest possible way to do this. We, by the way, are going to get to neural networks. Promise. I'm just going to take a few minutes. So this is known as one nearest neighbor. I switched musicians. Those are the Beatles. Do people know? Some people know. Okay, so this is John, and this is George, and this is Paul, and this is Ringo. Okay, here's the algorithm. So let's say we have a training set. So in the training set, we know that this is John, and this is George, and this is Paul, and this is Ringo. And now we have a new input. So the simplest possible thing that you can do is you could say, okay, for this new input, like, does this guy look like this? Or does this guy look like this? Or does this guy look like this? And so on. And then if you find that the image in the training set that looks the most like the new input here is this one, you look up who is this? Well, this is Paul. So you say this is Paul as well. So I think, interestingly, like this definitely is Paul McCartney, but I don't know if by just looking at those three images you can tell that this is the same person. But like if you don't know his face before, I don't know. But anyway, it is. Does this idea make sense? All right. So okay, so how do you do this actually with numbers? So how do you compare two images, like see whether they look alike? So there's multiple ways. So we already had this idea of the image is just a vector of numbers, right? So there's multiple ways of comparing different vectors to each other and seeing whether they're close together or far apart. So one thing you can do is just say, okay, like I have this vector and I have this vector. I can look at the distance between the endpoints of the vector. So for that, there is like a formula. So this is the distance between the endpoints. So the distance between the endpoints for images specifically might not be great. Does anyone have an idea why? Yeah. The origin is actually not really, because the origin is just a black. So the origin is like all zeros. So that's just like a black picture. And that's kind of the same for everyone. So one thing that you can think about is like, so this is like, you know, an image. So I drew a grid there that shouldn't be there, but this is like a small image with like 4 by 4 pixels, right? So if you multiply this by 0.5, it would be kind of the same image, just darker, right? But if you multiply it by 0.5, so even though it's the same image, the distance between the endpoints could be large, right? So in this picture, so this pole and this pole are kind of the same length, but if you multiply this pole by 0.5, it's still going to be pole, like it's just going to be the same image, just darker. But the distance between the endpoints could be large. So there is a formula for computing the cosine of the angle between vectors, and then the angle kind of doesn't care about the magnitude. Another way of thinking about the cosine of the angle is basically what you're doing is you're computing the dot product between A and B. So that's like the formula for the dot product. And then you're dividing by the product of the magnitudes. That's just the formula for the cosine of the angle as it happens. So if the magnitudes of all the vectors are kind of the same, that corresponds to the average brightness of the pixels being kind of the same. You can kind of just say, I'm just going to look at the numerator. I'm just going to look at the dot product and see if it's large or not. And then if the dot product between the two vectors is large, I'm going to say they're similar. And if the dot product is small, I'm going to say they're dissimilar. So that's because like the cosine of 0 is 1 and the cosine of like not 0 is less than 1. Does that make sense? So those are just like different ways of comparing images. So going back to this, what I could do is I could just say, well, I'll compute like the dot product between this and this, dot product between this, and so on. And I look for the dot product that's as large as possible. So, all right. I'm getting to neural networks, I promise. So sorry, I switched people again. Just so this is now a real data set that you can actually download from our website as well. So I have like 6 people, whatever, like Drescher, Ferreira, Chenoweth, Bolwin, Hader, Carell, whatever, like those people. And I have a new image, and I want to know which of those 6 it is. So here is the simplest possible neural network that you can have. This is basically logistic regression as well. So multinomial logistic regression because it's not just 0 and 1. So this picture, I'll give you the interpretation in neural networks terms for it as well. But it's basically a picture that corresponds to a formula. So the picture here is you plug in an image. So if it's a 64 by 64 image, it's going to be like pixels 1 through 4096. And you plug in like the first pixel here, pixel number 20 here, pixel number 4096 here. And then the arrows correspond to, you use X with this coefficient in order to compute Z1. And you use this X with this coefficient in order to compute Z6 and so on. So the formula is like this. So I'm saying multiply X by this W, multiply X1, sorry, by this W, multiply X20 by the W over here, and so on. And this is the formula, right? So W1JK multiplies XJ in order to compute ZK. Does that kind of make sense? So this picture just corresponds to this formula. And what we're saying is compute the Z1 and compute the Z3 and compute the Z6. We have as many Zs as we have possible names. And then we transform this kind of deal with the sigma so that it's a number between 0 and 1. And then, so far I haven't done anything. And then what we do is we make it so that when you plug in person 1, Z1 is close to 1, and all the rest of the Zs are close to 0. And when you plug in an X who's that corresponds to person 6, we try to make it so that Z6 is high and all the other Zs are low and so on. How do we do it? Well, the same way LM works. You just find the coefficients W and B such that it is the case on the training set most of the time that when you plug in person 1, then Z1 is high. When you plug in person 6, then Z6 is high. Does that kind of make sense? So when you're trying to do recognition, what you're doing is you're plugging in a new X, and you're then saying, well, like, is Z1 the highest, or is Z3 the highest, or is Z6 the highest? And then whichever output is the highest, that's the label that you use. So I'm gonna do like language models later. So here, I promise there's gonna be a framework in a second. So here's an interpretation of what's going on. So this is just a slice of this network. So what we're saying is, okay, like, we are trying to make it so that when the axes correspond to pixels from a picture of person 3, Z3 is high, right? So an interpretation here is that Z3 is going to be large when the dot product between this part of the W that corresponds to this W and this W and this W, when that dot product is large. So one way to think about it is going back to how do we measure similarities between vectors, is take this vector, which is constructed from this coefficient, this coefficient, this coefficient, and we're saying Z3 is going to be high when X is similar to this vector. Does that make sense? All right. So an interpretation of what's going on is, if this whole thing works, then that kind of means that this W1 everything 1 is a template for person 1. So we can try to see if that's true. So here what I did is I took a network like this that actually works, so it produces the right output most of the time. And then I took the W's that correspond to computing Z1 and the W's that correspond to computing Z3 and so on. And then I reshaped them back into an image and visualized. So the orange and blue is just to make it pretty. It's really black and white, right? So like orange is positive, blue is negative. And what you see is it kind of works, but kind of not. So those kind of do like faces if you squint, right? So that's good because I claimed that they're kind of like templates. But this does not particularly look like Alec Baldwin, I think. Also, humans tend to see faces in clouds and stuff like that, even if they're not there. It's like a known psychological effect. But those are like faces, right? So again, like, what's going on? So I just made a network like this, which corresponds to just a formula that just works on the training set and kind of works on the test set. And then I said an interpretation of what's going on is Z1 is high when the image X looks the most like this, and Z3 is high when the image X looks the most like this, and so on. Right? So that's just an interpretation, kind of like a visualization. So this kind of works, but it's kind of nothing. So what really works well is called deep neural networks. So this is the shallowest possible deep neural network. So it's a network with a hidden layer. The way it works is the same as before, but before you compute the outputs, Z1 through Z6, you compute what's called a hidden layer, which is an intermediate thing that's like the Zs, but just an intermediate step of the computation, right? So you plug in the image X into here, and then you compute H1 using a formula that's like this, that just corresponds to this picture. And you also compute H2, H3, and so on. Compute the K of those. And then using those, you compute the Zs. All right. So why do a hidden layer? Well, so one interpretation is that when you are doing this guy, what you're basically doing is you're saying, I have 6 templates, 1 template per person. And I'm saying, does X look like template 1? Does it look like template 2? Does it look like template 3? And so on. And based on that, I decide who is it that's in there. It kind of works if you do it for 6 people, but obviously kind of like me looking at you this way and me looking that way doesn't look very much alike, right? So 1 template per person is just too few. So the idea here is I can have as many templates as I want. So I can have K templates, and I'm kind of comparing X to template 1, template 2, template 3, and so on, up to K. And then based on how well X matches each of the templates, I compute the final outputs. All right. So again, another way of thinking about it is this is just a formula. So this is how you compute HK. I just decided that that's how I want to do it. And then this is how I compute the final. And then I just try to do the best I can on a training set. But the interpretation with the templates here actually works remarkably well. So if you visualize the templates that are used to compute the H, again, those are just coefficients that I choose to interpret as templates, right? They look like this. So this is kind of, so this is again, like just this formula that is made to predict as well as possible and then visualized. And what you see is that automatically the formula, the network that does the best, kind of automatically finds those kinds of things that kind of very much now look like templates because the network is now allowed to have as whatever, this is 200. Right? And what you see is that some templates, so now this definitely looks like faces. Some of them just look like particular faces in the training set. And the intuition there is this network, which represents a formula. Now it's allowed to just say, okay, I don't know what to do with this particular image in the training set, and I'm just going to memorize it. And then if the input looks exactly like that image from the training set, the particular H that corresponds to that is going to be high. And then based on that, I'm going to figure out the output. On the training set, that's going to work really well. Right? Obviously, on new images, it is not necessarily going to work well. So to summarize the story so far, so I started by talking about what's called one nearest neighbor. And this is the idea of just taking a training set and then for a new image to say like which image does the new image look the most like, based on that decide the. We then had kind of logistic regressions, zero hidden layer neural network, which you can interpret as I have as many templates as I have possible labels. I compute similarity using the dot product, and I pick the output that corresponds to the highest dot product, the corresponding templates. And then I have, so far we had like a one hidden layer neural network, which is saying I'm going to have k templates. And again, I'm going to match the template using the dot product. And then based on that, I'm going to say, okay, like based on the k matches, I'm going to, again, automatically figure out how to do a formula that takes how similar is the input to each of the templates, and then decide what the output is. So it kind of all fits in the same framework, you think. Make sense? So the last thing I'm going to say is, okay, like how does it all fit with like the word neural network? Well, one, it's a metaphor. It's like, it in a way is just a formula, right? But the idea is kind of like this. So you do have kind of light receptors on your retina, right? So like a ray of light hits your retina, that activates a cell in the retina. That in turn, we know at least about the cat, it does activate neurons in your visual cortex. The idea is that when the neurons in the visual cortex activate, that makes it so that other neurons in other areas of your brain start activating. So the picture here is kind of inspired by this, right? So the picture here is the axis kind of corresponds to the light receptors in your retina, right? So if this pixel is light, x1 is going to be high. If this pixel is dark, then this one is going to be low, right? And then you can kind of think of H1 as being kind of a neuron in your visual cortex, right? So you might imagine that there is this neuron in your visual cortex that activates if the input X looks a particular way. And the specific interpretation was like we have a template for it, right? And then the idea is like somewhere else in your brain, because this neuron and this neuron and this neuron activated in a particular way, then somewhere else in your brain, there's another neuron that activates because it's this particular person. So again, kind of what we actually know about the brain is definitely in the visual cortex. That's like very clear, kind of, like edges, stuff like that, that does activate particular neurons. We do know that neurons kind of deeper in the brain as in the visual cortex as it were, do activate based on more abstract concepts. That does kind of happen. Cognition in general, we don't really know. So there is not like a neuron that lights up because someone says neural network to you. That's not the thing that happens. Yeah, all right. I think we're done for today. Thank you very much. I'm back in Toronto. I'm gonna be in touch. I'm sorry that Gradescope is like flaked out on me. I'm trying to fix it. If you nobody emailed me complaining that they forgot what they said about their project, but if that's an issue, let me know. Otherwise, I'll try to mark everything by Friday, hopefully. All right. Thank you.